Okay, in this video, we're going to be going through some revision materials for Stage 2 General Maths, and the particular revision materials are on statistical models, so bivariate statistics as well as normal distributions. All right, just check my microphone seems to be okay. All right, so let's get stuck into this. Also got my calculator ready as well to go when I need it. All right, so let's start. So, first question. The Australorp chicken produces eggs with weights in grams that are normally distributed. With mean of 56 grams and a standard deviation of 4 grams. The eggs are classified as medium, large, extra large according to their weight in the table alongside. There you go, a table. Okay, first question. The normal distribution of the weights of the Australorp chicken eggs is graphed alongside. Copy the graph and clearly write the horizontal axis, numeric axis. All right, so mean and above and below standard deviation. Okay, so we're filling out this one. I've gone and copied that one. So our mean is 56. So let's go and put that in. So right here, we'll put in 56. Okay, all right. And then we are going up and down by 4 grams. So where the inflection point joins, that's up by 4 grams. We now have 60. And just for the sake of it, I'm just going to do it this way. 60, 64, and 68. So you have to go up 3. All right, and there we go. I'll make that a little bit more level with that. Okay, something to that effect. Good enough. And then on the other side. So let's see what we can do. All right, a bit more challenging to go down. All right, so we had 54. Go away, Grammarly, I don't want you right now. Okay. So we got going down by 4, 52, 48. Move that down a little bit. Yeah, 48. And down here, we will have, all right, another 4 down is 44. Okay. Something to that effect. There we go. Okay, not bad. Okay, on the graph alongside, show the area that represents the proportion of chicken eggs that are extra large. All right, so above 60. So what we could do is we can do a little line. Do I have a line tool in this thing? I don't think I do. Nope. Okay. We're just going to freehand draw that. It's a bit wonky. You get the idea. And maybe we'll get a highlighter in here. Okay, so all that area in there. So everything above 60 is that part. Okay. So, okay, so the extra large, yeah. Okay. Egg chosen at random. Find the probability the egg is medium or large. Okay, let's go medium. So we have medium is below. So we want to find the probability of X being below 54. Okay, that's medium. Oh. Right. So get our calculator, and we are going to go into second distribution, normal CDF. All right, so medium is everything below 54. So our upper is 54, and lower is just going to be, we'll do a negative number. We'll just do negative 1,000. That should do the trick. All right. So we had, mean was 56, and 56, and standard deviation of 4. All right, calculate that. All right, so it's about 30.85% or 30.9%. So we're going to put that in. All right, so 0.85. 0.3085. So I'm going to round it off to 30.9%. All right. All right, probability. You can write it as a probability or as a percentage. That'd be fine. Let's do large. Similarly, okay, so large falls inside a range, so it falls in between. So probability, it falls between 54 and 60. Okay, let's just do that calculation. Or CDF. 54 and 60. Okay, the rest of that. 53.3%. Copy that out. All right, so we've done, that was part C. This was A and B. Right, D. There's a probability of 2% the egg weighs more than K grams. All right. So probability X is greater than K equals 0.002. All right, or 20%. So how can you go about doing that? There's two ways. You either do that as a right tail, or if you don't have the ability to do a right tail, let me show you how you do that. We can subtract from 1 and change the argument the other way around. So if 20% of them if there's a 20% above K, then there must be an 80% below it. All right, so then 0.8, and that will be using the left tail, which is how some of the ordered calculators are set up. All right, so either way, okay, K equals. All right, let's go on our calculator. All right, so we're doing inverse normal. All right, so area 0.2, mean of 56, standard deviation 4. I need a right tail from doing it that way. Okay, so 59.4. 59.4, and the context is grams of G. All right, let me just double check if that works the other way too. So if I go this way, go inverse normal, 0.8, and make that a left tail. Yep, same result. Either way, 59.4 grams, and that's question 1 done. Or first question here. They are differently numbered because they're pulled from a different resource. Schedule scatter plot. In your assessment, you're expected to do one by hand. I'm just going to do everything on the calculator because this is not the most nicest of numbers. All right. Maximum temperature versus number of bottles, soft drink, data above. All right. So let's go enter this into our calculator. Okay, let's get rid of, delete everything. All right. So 20, 23, 24, 27. Let me give it a screen a bit better. 29, 31, 32, 33, 34, and 36. Number of bottles sold each day: 152, 186, 193, 247, 290, 301, 319, 3, 4, 6, 375, 389, and we've got it. I'll double check those. Looks alright to me. Alright. We should take a little bit more care, just make sure. 1, 36, 34, 33, 32, 1, 30. Yep, looks great. Alright, so do a scatter plot. So we're going to do a stat plot. That's already on, excellent. I'll need to set my window accordingly. Yeah, you have to do a skew graph. I'm going to start with 19, because this is just going to be a lot of wasted space otherwise. If we include 0 on the axis, our maximum appears to be 36, so make it a little bit wider than that. So it's the other data point, 38, or maybe just 39. Y min, okay. Well, again, I'm gonna have to jump up a bit. I'm gonna do 1, 4, 5, and I'm gonna go up to 400. Just give a little bit of a buffer above and below the actual data just to see all the points correctly. Let's see what happens. Okay. And you can count your points to make sure you got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I can see all of them. All right. Okay, so for the sake of it, I'm just going to paste that there as... Actually, I can't do that on here, can I? Oh, boy. I can't insert a image on there. All right. Determine this... So I'm just going to have to answer with B. So you can see in the video, you can see that there. Okay, I can't paste that in like a Word document. All right. Regardless, can't be helped. Okay. So determine the describe the association between maximum temperature and number of bottles sold using Pearson correlation. Okay, so we've got a wrong thing. Let's go and work that out. So we're going to stat calc linear registry. Go down to actually do it that way. Do 4, not 8. Yes, so list 1, list 2, and you calculate. Okay. So you have a very strong positive correlation. All right, so down. Okay, shut that down. 0.9, what was it? 9871. And R squared is 0.9934. Okay, so strong positive correlation. Okay, that's for B. What's the reason we would apply an equation least square regression line? What's the reason we would apply an equation of the least square regression line to fit the data? Basically, because it is a strong. Yep. Okay. Right. Yeah, basically, you can also test you will have to say the equation line which fit. Does the residual confirm linear model fits the data? Okay, I have to show that. I can't print that on the screen, so we'll go through the residuals in a moment. Basically, you can also put the argument that the residuals. We haven't done it yet, but let's just make the assumption residual. Okay, so I haven't done it yet. I might have to change that answer in a minute if I'm wrong. Um, okay, state the equation least squares regression line. Okay, all right, so D. Okay, the equation is y equals 15.58 x plus minus actually 170.5. Okay, so four in figures. Okay. Does the residual confirm that? I'm gonna write the assumption as well. So I'm getting cart before the horse. I'm assuming just from the how good this is, and because the question's not asking us to do an exponent, that residual. We'll see this in a minute. We'll prove it. Okay, so residuals is get randomly. See, there's there we go. Okay, I'm making that assumption now. We're going to show it in a minute. Okay, because it didn't ask us to do. Okay, but we'll look at the residuals. All right, so okie dokie. Now we've got that. We're going to go to our y section and we'll get rid of this, and we'll go 15 point. Variable. Yeah. And you already can kind of see it here. You can see, okay, that one's above, that one's a little bit below, a little bit below, close, above, below, close, above, close. So there's a nice scatter there. For that line of best fit, but let's go prove the residuals. You don't have to calculate the residuals, so we might take this shortcut way of doing this. I remember how to do that. I think we do stat plot, and we're going to plot wireless. We're going to change that. Okay, I think we go. What do you want? Go away. All right. How do we do that? We're going to variables. Y-vars. Nope. How do we do that again? List, I think. There it is. Yeah, list. Second list. Do residual. Wireless residual. That's a shortcut way of doing this. We're also going to have to change our window. So you have to do this with negatives. I'm gonna go -5 and then +5 for the y and see what happens. So we're now gonna look at our residual plot. Okay, don't see enough points. So you got 1, 2, 3, 4. Let's make our y a little bit larger. All right, window -10 to 10. So make sure you can see all your data points. All right, 1, 2, 3, 4, 5, 6, 7. All right. So we have to go larger than that. All right, window 20, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we can see them now. And what we can see is the residuals scatter randomly along the line of best fit. There's no particular pattern here. There's down, up a lot, down a bit, down a lot, down a bit, up, down, a little bit up, a little bit down. That's random. So that's what I put in here. Residuals scan randomly around the line of best fit. Okay, so that was part 1. Okay. All right. So you can do these sections on the calculator as well in the graphing section. So to do that, I'm going to have to go back. I'm going to turn my stat plot actually off. And I'm going to reset the window to what I had it before. Okay, and you could just go and plug the numbers into the calculator and do it algebraically, also by substitution. But since I've got the calculator here, I'll demonstrate this. All right, so what did I put here? I put 145, and I think I put 400. Okay, so now I'm just looking at my line best fit. Okay, so I don't have my data points on there anymore. I've turned them off. Okay, so part two. So D. Okay. Suppose the maximum temperature on 48 degrees on one day, so 28 degrees. Use the equation for that. Predict number of models of the drinks sold. Okay, so when x equals 28 degrees, y equals. Let's go and figure it out. Okay, easiest way I think is just can you just type it in 28? Nope. No, that's this. No, you can't do it in that graph. All right. So let's do a trace. I think if you do it now, if I type 28 into my trace, I can go and work that out. So it's about round to the nearest. It's appropriate in this instance to round to the nearest soft drink can. So it'll be 266 cans. All right. Sold. If you want to be really particular. All right. To part three. Ba-ba-ba. Okay, suppose that 125 bottles are sold on a particular day. Use the equation part three. Predict the maximum temperature, and again, you could go and equate that. You can let your y equal 125. The way to do that on your calculator, you need to find an intersection. You set up a second one that goes 125 cans sold. Graph that. We do not see that. That's because it's down here somewhere. Okay, so we need to change our window. We need a bit more negative space. Actually, we need white space. So I made that, and maybe I might make that a little bit shorter as well. So it's because it's lower. This is actually extrapolation in the smaller side. Okay, there it is. Yeah. So we're going to do a calc. We're going to do an intersection. Okay, and there's only two things to do anyway, so just let it do its thing. Yeah, so when y is equal to what did it want? 125 x equals and you can approximate that as well. It's 90 degrees. Discuss reasonableness. Okay, so I'll say part II is reasonable because interpolating so if we're interpolating models for high R squared models for a high R squared model and subsequently part I'll say is less reliable. So remember, interpolations when you're predicting things that occur within the range of your data set. So when we were predicting 28 degrees, that fell inside our data set. When you do 125, that falls below the values that we got. So that's extrapolation. I'll say but close to. So you still gotta. It's okay to extend because it's like 1 degree less effectively, and it's like about 25 cans less than what's in the data series. It's close to it. R square's high, so it's somewhat reliable, less reliable. Make a comment about the fact you're extrapolating versus interpolating, and you got the idea. Okay, and that's all of it for that question. So let's move on to the next one. All right, so we have another modeling question. All right, identify. Okay, so we got plants were sprayed different various concentrations of new pesticide after 2 weeks. Number of dead bugs in each plant were counted, and results are shown in the table below. All right, so let's have a look. See, okay, outlier. That would be your outlier. So that's your outlier there. Okay, there's your A. Oh, that one. I already did it. Oh, never mind. Oh yeah, there we go. Yeah, move you closer. There you go. All right. So that's the furthest away from the line of best fit. Is an outlay an error? So just one possible reason for this error. I think this really comes up in that we could say it's yeah, to write anything essentially intelligible for that. So let's have a look to part B. As we say what lowercase. There we go. Um, I'll just come up with something calibration error. All right, part B, part one. And you can come up with anything you like for that. That kind of makes sense. If the outlier is used in error, okay. Yeah, actually, sorry, we just did that. Actually, we didn't do part one. Calculate. We actually have to do GIS calculation. Oh, okay, that was actually my bad. I wasn't reading it properly. That's actually a B. BI. Hmm. All right, so we have to get calculated and punch in some more data. Oh well. Okay, let's go into stats. No, I don't want list. Quit. I don't want you either. Stat. Okay, edit. Punch in the data. Okay, we've got 9 plants. Cool. 25, 36, 50, 52, 56. Oops, 56, 64, 72, 80. Ba, 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 ba. Dead bugs. Okay, 2, 39, 19, 38, 53, 51. What's this stuff? It's up. 38. What have I done? Stop it. I want to scroll down. Okay, 38, 39. Sorry, that's reading ahead. Then 38, then 53, then 51, then 66. Okay. Check this going up. 60, 55, 51, 53, 38, 39, 38, 19, 39, 2, 10, 25, 36, 50, 52, 56, 64, 72, and 80. Okay. So let's just do our. Okay. I don't want that anymore. Turn off. Stat. Calc. In reg. Right. Okay, so part A, you got to ask, it just asks you for the R squared. Okay, so that is at A R squared equals 0.797. Dunskies. Okay, that was actually part 2. Alright, C, part I. Remove the outlier, recalculate the coefficient determination. Okay, so we're going to go back into our data set. So removing the second data point. Okay, so we can go delete and delete. Yes. All right. Then we go quit, stats, calc, linear registry, recalculate. All right, and now we get a 0.968 r squared equals. That's 58, wasn't it? All right. Okay. Interpolate string association, so is a strong correlation. A very strong correlation. All right. Okay. That was part 2. All right. Determine least squares regression line with the outlier removed. Okay, so let's go into that. We've got it all there. D y equals, all right, 0.903. Maybe I'll have to do 4 seven figures. 9029. X and minus 9150. Actually, hang on. Was it 0.9150? No, it wasn't. It was 9.150. There we go. Double check that. Okay. Yes. Yes. Okay. Let's move on. All right, so that was D. Using the squared regression line, determine party. Predict the number of dead bugs. Okay, so spray concentration was 49%. Okay. All right, this is actually very similar to the previous question, I must admit. Okay, so maybe it's a little bit redundant. Okay. So the idea of the outlier is probably the only thing that's kind of different about this. You're doing some extra interpolation and, okay, actually no, we only do interpolation because that is 49 falls inside there. All right, so part E part. Now, I'm actually just going to punch this in because, all right, so I'm going to go in straight up substitution. So we're going to do X is equal to 49, which is the concentration percentage. I can actually, I'm going to move this over here so I actually can see better. All right, and I'm just going to do this by substitution on my I'm still going to use the calculator, but I'm not going to bother with the graphing section. I'm going to go straight to here because I don't have to do anything else with that. Okay. All right, so then I can just go and substitute in 49 in place of X and do that multiplication. Minus 9.15, okay, which will be equal to, all right, so get our calculator out. We're just going to go into our run section and calculate it that way. So 0.9029 times 49 minus 9.15. All right, so you have, I'm going to round it to the nearest bug, 35 bugs. Dead bugs. Dead bugs. There we go. All right. Damn dead. Okay, so 49% predict the number of the. Okay. Okay, so another reliable question. Oh, they calls it accurate. Yep, accurate because of that. There you go. Okay. Part 3. Assuming sample size is appropriate, set one of the factors that could cause the prediction you made in part 1. Because one other factor I'm thinking of is the value move. So you could say value remove of non-ally, it was due to randomness. So maybe you might say the spread is unpredictable and that wasn't an outlier. Like you could do a similar experiment. I suppose that's kind of what they're saying about the sample size. Is again, it's a question you can kind of interpret a few ways and give an intelligible answer and get a result. It's not because we're extrapolating; it does fall inside the data set, so it's not that. All right. Okay. But those are some of the reasons. All right. So let's move on. I think that was it. Yeah. Okay. All right. Testing been carried out. Links. Smartphone battery will work up to 2 hours because it needs charging. All right. Mean life of that. And using that, all batteries are fully charged before testing. All right. All right. Okay. So battery hours 16. Squeeze that in there. Point. No, I'll do it. I'll type it. 16.3. Boom. 16.3. 30 24. So that'll be 18.7. 16.3 plus 2.4. I think that's 13.9. 13.9 plus 2.4 would be carry the 1. Yeah, that looks right to me. Okay, I think that's right. Franco's percentage brand X batteries are expected to last less than 15. Okay. All right, so finding the probability that X falls less than 15. Okay, B part Y equals, all right, calculate time. So back to our distribution, NCD. Okay, we are doing last less than, so that looks right. Okay, 15. All right. Mean of 16.3 and standard deviation 2.4. Okay, 29%. Okay. Okay, so the last one. So you buy that many batteries, how many would you expect to last us 15 hours? Well, it'd be 29.4% of, so it's for part two. I was at 834. You basically just multiply by the proportion. It's the easiest way to just go about doing this. Times by, okay, so let's go back into that. I think you can just take your last answer and do that. So I just calculated an answer. Can I just do multiplied by 834? Seems I can. All right, probably approximately 245 batteries. Okay. Is that it? Yep, that looks like it. All right. Brand X advertisers claim that 90% of their smartphones will last at least 9 hours. At least. So you have 90% of the graph, and it's at least. Okay, so it has to be, so that has to be the minimum. So then the one that's correct is this one. There's a big chunk of the graph, and it's at least 90% of it. All right. Calculate the value of t. All right. Okay. So we've got the same values as the same brand, so we're just doing an inverse normal with those variables. Okay. Fortunately. Okay. 90%. All right. What was it again? 13.9. Oops. No, it's not. It is 16.3 and 2.4. And this is a right tail. Okay. 2.4. Okay. So what we're saying here, I'll put it underneath. All right, T part two. Probability that x is greater than k has an area of 0.9. Okay, k is equal to, catch it out, 13.22 minutes, or hours, actually, hours. That's part two. All right. Manufacturers of brand X batteries extend their testing due to rival brand smartphone battery, blah blah blah. Brand Y and brand Z. Okay. It was found that T normally distributed two rival brands. Brand Y has a mean life of 18, standard deviation of 3. Brand Z has a mean life of 21 and 4. Okay, so let's have a think about this. This is going to be a higher variance, so that's wider. Okay, so brand Z has to be on the right of Y because of that. So that one, the peak would be, so that would be peak left, and the other one's peak right. Yeah. Okay, and then this one is 3 hours. That would be narrow and tall. Okay, so keeping that in mind, all right, which one's which? All right, so let's get my little pen out to tick which one I think is correct. All right, brand Y, okay, brand Y is on the left. It is not as tall and it's wider. Okay, brand Y, so that one is out. Wrong. This is also wrong because they appear to have the same mean. Okay, well I said, okay. Brand Y is on the left and it is taller. I believe that's the correct one. And we'll see if we can dismiss the last one. Brand Y is wider and shorter, then that's wrong. Okay. So that is the correct one. There we go. Okay. Yeah, you just had to circle that one. I put a fair bit of work into explaining it. So hopefully now you understand why. Okay. All right. So we've got another one with some residuals and things of that nature. So we have outbreak of contagious disease. Okay. Days of the first case. All right, yep. All right, so scatter plot, there's done it for you. Select the graph which shows the best line of fit for a linear model. Okay, that is not a linear, that is exponential. That one fits very poorly. You have more on the bottom than you do at the top, so it's a bad fit. You can't do multiple linear lines, so by process elimination, that is the best one. Okay, so D. All right. Alongside the graphs to the residual linear plot, using the residual plot above, give 2 reasons why it's not appropriate to apply a linear model to that. Okay. Okay, I'll see. All right, the main one is that residual. They follow a pattern. So you don't have the random scatter. There's an obvious pattern. Okay. And you could say there appear to be a. Okay, so we're talking about. It's hard to say. It's like when you say it's a poor fit along there, they've got values that are very high. So we've got residuals of 40s. That really has to do with the magnitude of this. Although for smaller values, if you're getting something in there, like the early data points, if they're out by 40 and 20 on the model, and we're only dealing with like numbers like 2 and 3, you can say the bad fits. Yeah, relative to the data. Okay. All right. What else? Determine exponential model data and context. So now we do have to pull our calculators out. All right. Okay. So we haven't done the exponential one yet. So let's go edit. Scroll back up. All right. Get that data in. Delete. Stop it. All right. 2, 5, 12, 20, 26, 33, 41. Okay. 3, 8, 25, 47, 100, 1, 2, 5. Okay, boom skis. So let's go and stat plot that. We need to change our window. So I'm going to go 0 to 43. And I'm going to go from, yeah, I'll do 0 as well, to 350. Okay, graph that. No, I don't want that, sorry. I want, okay. Let's turn those off. I might have to delete them later on. Go into stat plot, turn that back on. We do not want residuals, we want list 2. Okay, graph. I didn't turn my step plot on, did I? On. There we go. Yep. And then we can go. Oops, that's what I wanted. I want to start. I want to go into calcs, and I want to do exponential, expreg. Okay. All right. Similar models of data, and that'd be of constants are in context of data. All right. So y equals 4041. Okay, times, okay, what's the other number? 1.125 to the power of x. All right. Sorry, I can't do superscripts in this. I have to look like that. And those are multiplied. So that was C. Okay, C part 1. C part 2. The A value is the approximate. So approximate use cases on day 0. And this is 1.125 is the growth rate. So there'll be a 1. If you subtract 1 and times it by 100, you have 12.5% increase per day. Okay. All right. Now I'm running short on time. I need to go to a meeting. Calculate the number of new cases of disease recorded on the 60th day of the outbreak. So let's just do, okay, so x equals 60. All right. And then I'll have that second one is y equals 1, 10,000. All right. Okay. All right, so let's see what we can bust out in the next couple of minutes. All right. Okay. So let's go to y equals, and you had to delete those. All right. I'm going to put that one in though. Okay, whoops, too many zeros. So I'm getting ahead of myself. And now I'm doing this one, 4.041 times 1.125 to the power of variable. Okay, graph these. All right, so yep, there's our model. And we can't see that in the window because we need more space. All right, we go in from 0 to, all right, we want to have at least 60, so I'll go to 61, and I need my y to go to 10,000. Okay. Ooh, I need a lot more space. I need a lot more x space. Window. Let's go to day 100. Let's do 120. That should be plenty. Yeah, that's actually probably a bit too much. Let's just do 90. That'll do. Yeah, you can barely see these now because we've zoomed out so far. There's a lot of extrapolation there, so you'd be commenting on the unreliability of that. But we can do trace, and we'll do a trace 60. You need to. I didn't take my data points off, so you have to tag over to those. So we've got 60th day. 60 is 10,000. No, it's not. Oh, I know why. Okay, because I'm not clicking on the right thing. Sorry, I've got too many things going on here. All right, so I need to click on the blue graph, then do my trace at 60. Yeah, it's already done it for me. So on the day 60, the number of new cases is y equals 4,738. So we've got this is di. Okay, d double I. All right, so now I want to solve the intersection of this. All right, so calc intersection. Yes, 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 yep. Day 66. Okay. Calculate how long it takes for it to double. All right. Okay. A couple ways you can go about doing this. One is I might just go and since I've already got 10,000, I want to go find. What if I went and found 5,000? All right, so there should be consistency with exponentials in terms of doubling rates. So if I graph both of these, I find the intersection of this. So I let y equals 5,000, and then I find my x value. This should work. This sort of stuff works for exponentials. All right. I could go and find where it hits 8, but I think this would be more reliable. You get a better answer. Okay, so let's go intersection, calc, intersection. Just make sure we get the right function. I've got a lot on my screen. I need blue and black. All right. 60.4 of 60.5. Okay. Okay, so if I went and subtracted that, look, I'm going to round it off the difference. So if I go 66.3 minus 60.5 is equals about approximately. So I'm going to approximate to the nearest day, because this is counting days anyway. I've done some decimals, but I think yeah, I think it's appropriate. Approximately 6 days. Okay. Explain why exponential models might eventually become unreasonable. The short answer is you're going to run out of population. Okay, so eventually everyone's going to get it, or at least you get a large amount of the population. If you're curious, the actual model, we don't teach this one in this course, but the actual model is actually looks like this. It kind of, oops, a little bit, nah. It's logistic. It goes up like an exponential and then bends over and flattens out to a maximum. Yeah, about that. That's straight. Okay, I got a bit wonky, but that's not necessary for the understanding here. Okay, so that's going to be my video. It's a good bit of time. I am now out of time, so I'm going to leave the video there. All right, see you later.